Okay, now here you want to find a general solution to this differential equation, and oh, look, you're not being told what the solutions are. All right, take a moment to copy that down, that example. Okay, so, well, what we have to do is we have to try to think about what a good guess would be. What would a good guess be? Now, this is a homogeneous differential equation. And notice that for this differential equation, notice that all the coefficients of the derivatives and the coefficient of y here, they're all constant coefficients. So what you're going to learn here is on how to find solutions is specifically for linear equations, homogeneous linear equations, in this case for 4.3, where you have constant coefficients. So here's what we're going to do. We're gonna make a good guess, okay, and then work with that. So remember the previous problem you looked at? You had a differential equation, and they told you that, you know, like e to the 2x was a solution. And this is for the section 4.1 problem we just looked at. They told you e to the 2x, e to the 5x were solutions to the homogeneous differential equation. Matthew remembers it. Well, what if we were to consider solutions that might have the form e to the mx power? Now, that solution would only be a solution if we could solve for m. So let's sort of go down that road and see what happens. So, okay, we're going to try a solution of the form y equals e to the mx power. So since we have a second degree differential equation or second order differential equation, we're going to need to get the first and second derivatives of this candidate solution. So let you copy up to here, okay, and then I'll continue. Let me know if you have any questions. I want you to, I don't want to go too far ahead of you, okay? So, yeah, Zachary, you're going to see why e to the mx power works. And Ann, you're going to see why. You're going to see why it works. You're going to be kind of amazed, actually. So hold that thought. Okay, so we compute the derivatives, and now we're going to substitute the derivatives in that differential equation. Okay, so here's the differential equation, and now we're substituting y prime, and y double prime into the differential equation, and that's right here. We did that right here. And remember, we're trying to solve for m. If we can solve for m, if we can find a value or values for m, then this was a legitimate guess, good guess. So we get down here to this equation, and again, if we can find values of m that solve this equation, then our guess worked. So, okay, I'm looking here at this equation, and what's the common factor on the left side? Whenever we solve an equation, we think about factoring, right? So what's a common factor on the left side?
E to the mx.
E to the mx. That's right, Michael. So we can factor that out. We can factor that out. And so that's what we did. And we get down to here. Get down to there. Are you optimistic that we can find value or values for m now? Now that we've factored the left-hand side of the equation? All right. Well, you know what? Let me ask you this. Let me ask you this, okay? And I appreciate Zachary's thinking on this. If you had, let's just say you had this. Let's say that you had A times B equals 0. Let's say you had this equation, A times B equals 0. What does this imply? Either A equals
0 or b equals 0.
0, good, right, Michael, or
b equals 0.
or B equals 0. Okay, so if you have, I want to say this the way I want to say it here. If you have the equation A times B equals 0, that's going to imply two things. Either A equals 0 or either B equals 0. Right, and so can't we do the same thing here? Can't we say, all right, either e to the mx power equals 0 or 2m squared minus 3m plus 4 equals 0? I mean, can't we do the same thing? Yeah, and that's absolutely, and that's what we're going to do. So on the next page, indeed, this equation implies either e to the mx power equals 0 or 2m squared minus 3m plus 4 equals 0. But the thing is, for the first equation, an exponential function, e to the mx power, is never going to equal 0. That has no solution. How many notice exponential functions, either they grow or they approach like the x-axis? You know, remember your exponential functions? You know, exponential function. Okay, depending on the value of m, you know, well, hold on, I can do a little better than that. You know, here's an x, here's a y. exponential functions look like this. This would be when m is greater than 0. Or exponential functions look like this when m is less than 0. How many recall that from your pre-calculus days? Sure, sure. Thank you, Christopher, Ann, and Matthew. Absolutely. So there's no solution to this first equation. Thank you, Andrea. But this second equation, 2m squared minus 3m plus 4 equals 0, that does have a solution. And that's called our auxiliary equation. Our auxiliary equation. And notice that the original differential equation, the differential equation that we're trying to find solutions for is 2 times y double prime minus 3 times y prime plus 4 times y equals 0. Isn't that kind of interesting? Our differential equation was 2y double prime minus 3y prime plus 4y equals 0. What's kind of interesting when you compare the differential equation to the auxiliary equation? What do you notice they have in common? Well, the degree, okay, all right, Thomas. And what else matches? The coefficients. Good, good. Hyung, Andre, Ann, and Thomas. That's right. 2, -3, and 4. And that's going to be true. That's going to be true. So what this means is when we have a homogeneous linear equation with constant coefficients, we can just go right to the auxiliary equation. We can construct the auxiliary equation immediately and then solve for m. But I just wanted to show you kind of where that auxiliary equation comes from. Okay, well, we solve for m. Now this, of course, we love to factor, but this quadratic equation on the left can't be factored, so we're going to use quadratic formula, and we end up getting complex roots. We end up getting complex roots. And it turns out that the general solution to this equation is going to be given here. Now you're wondering why. Where'd that come from, Dr. Duty? I'll show you. But just go ahead. I'm going to show you why that is. If you think about the solution for m, you have an alpha plus I times a number we'll call beta. The general solution is, the alpha and beta occurs again. And I'll show you that a little bit later. But let's just, I want to make sure you're comfortable. Let me know if you have any questions. I'll give you a chance to, another moment to copy that. Okay, so there are three cases that we have to consider. Three cases that we have to consider here. May I go to the next page? All right, Andrea's good. Jonathan's good. All right, so how do we get these solutions? All right, so this comes from the textbook, but I wrote it out a little bit for you because I thought it would, I just wanted to write it out. There are three cases that we have to consider for the roots of an auxiliary equation. So am squared plus bm plus c equals 0. That auxiliary equation is going to come from the second order differential equation, ay double prime plus by prime plus cy equals 0. But there are three cases to consider because the auxiliary equation, that auxiliary equation, am squared plus bm plus c equals 0, you can have three different kinds of roots. You can have complex roots. You can have real roots, different real roots, and then you can have repeated real roots. And depending on which case, that's going to determine what the solution looks like. That's going to determine how the solution looks. Okay, and in the book, they let me just see here, one moment. In the book, they go into some detail on proving this, but I want you to just sort of intuitively, you're going to be comfortable with it. So first of all, case one, when you have two distinct real, let me put that in blue, two distinct real roots. Okay, case one. So when you have two distinct real roots, the solution of the differential equation, well, first of all, the solutions would be E. The solutions to the homogeneous differential equation would be e to the power m1 of x and e to the power m2 of x. But because m1 and m2 are different, these two solutions here are linearly independent. And so the general solution would just be then, by the superposition principle, a linear combination of those two homogeneous solutions. Okay, so that's case one. Now, what if you were to have a repeated real roots? Okay, well, that's the second case. So again, what you want to do is you want to construct your general solution, but in this time, the one solution is going to be e to the m1, e to the power m1x. The other solution is going to be x times e to the m1, e to the power m1x. Okay, and we have that x inserted because we need linear independence of y1 and y2. You have to have linear independence. So again, you're looking for a fundamental set of solutions to the homogeneous differential equation. A fundamental set of solutions, those solutions are linearly independent. And so you can't have the solution e to the m1x power twice. You can't, because then you wouldn't have linear independence between y1 and y2. So that's why we insert the x there. Okay. That's why the x is inserted there. Repeated root means, and like if you were to have something like, let's say you had, you were able to factor your equation, and you'd have like x minus 2 times x minus 2 equals 0. you'd have a repeated root. Okay, no problem, no problem. Okay. So this idea of linear independence justifies why the x is there. Now, to formally prove it, there's a proof, but intuitively you know that you have to have a fundamental set, you have to have linear independence. The third case is the case where you have conjugate complex roots. Complex roots will always occur as conjugates. And so if you have alpha plus or minus I times beta, the general solution of the differential equation is outlined here.
Like, where did you get this, though?
It's proven, it's actually proven in the textbook.
Okay.
It's a good question, Matthew, and I wish we had time to, if we had time, we would be able to show it. But if you look in your book before example 1, in section 4.3, if you look before example 1, the case 3, the complex conjugate roots, they actually prove it using a Euler's formula, and it's pretty cool. But for in the for the interest of time, we'll let that go for now. Maybe on Thursday we can peek at it, all right, good question, good question. So a lot of times, sometimes, I mean, proofs are good of things. It's nice, but yeah, master's looking at the proof. But sometimes, I always think there is, if you can get an intuitive feel for the math that's going on, that helps you then understand the proof. All right, are there any questions on this? And these are the 3 cases. That's it. Those are the only 3. Those are the 3 cases. All right, may I go to the next example? Okay, give you another minute here. No problem. Okay, hold on, there's a question here. Yeah, Zachary, how did you know how to use e to the mx power? Yeah, I don't, I mean, trying to think on this, how did we come up with that? I mean, clearly it is very possible that, a couple hundred years ago, say, somebody said, let's try that. Let's see if that works. And it worked. In other words, I mean, no, that's not the best answer. I wish I could say formally, how did they come up with that? Zachary says, how did we know to use e to the mx power? I have, offhand, I don't know if that was basically, something that a mathematician long time ago came up with and it worked. I'm not sure about that, but I'm trying to think if maybe, it's a wonderful question. Let me think on that and try to get back to you on that. Okay, Zachary, see if there's any sort of information on how that was inspired. Does that sound good? Yeah, so okay, and Michael says he's heard that from other profs that maybe it was trying to, well, you know, like mass spring systems, for instance, like these differential equations. There's a reason we have these kind of differential equations. If you look at harmonic motion, a mass spring system, we'll get into this in section 5.1. 5.1. A mass spring system is a second order differential equation, and the motion of the mass behaves a certain way, the position of the mass, and maybe through observation, that based on the position of the mass, mathematicians were sort of clued in to what could possibly be solutions to the differential equation, and that guided them as to this e to the mx power solution. That Michael's saying by experience, and that's what I just, so I think that's a reasonable, certainly reasonable. Good questions, everybody. Let's do another example here. Let's do another example. Oh my goodness, look at this example. Look at this example. We want to find what's the order of this differential equation. All right, it is of order 5, the fifth order differential equation. Now, notice that the coefficients here are all constants. They're all constants. And we're going to find its general solution. All right, let me give you a moment to copy it down. Okay, so what's the first thing? What's the first thing? I'm wanted to give students a chance to copy, Zachary. Now that people have copied, and you know, when I generally like to, well, you know, if I'm giving you a chance to copy, I let you copy. So okay, so what do we have to do here? Okay, Michael's right. We have to get a 5th degree polynomial auxiliary equation. Okay, what would it be, by the way? What would the 5th degree polynomial auxiliary equation be? Think about it. I think you know what it is. It's going to be this. 2m to the 5th power minus 7 times m to the 4th power plus 12m cubed plus 8m squared equals 0. No problem, Zachary. No problem. No problem. Zachary, it's going to be in the recording, so you'll be fine. You'll be fine. Thank you for letting me know. So how many remember in pre-calculus solving polynomial equations of high order where you had to use like the rational root theorem? You know, you had to look at like P over Q and look at the coefficients of the first and last term and the rational root theorem. How many remember? And then, you know, making guesses and using synthetic division to break down the equation. Zachary Zachary remembers it, mildly familiar. How many remember doing that kind of thing?
I can't say I remember that.
All right. Well, you know, you've lived a lucky life, Justin. Michael remembers it. Matthew vaguely. Well, you're in luck here. We're going to use a MATLAB program. So we're going to solve. And Christopher remembers some time ago. So you are going to be able to use a MATLAB program to solve this auxiliary equation. All right. And let me just show you, I mean, you're up to here. Let me show you the MATLAB program here real quick, and then I'm going to come back to this. Let me get it here. One moment. Let me get it. Okay, so let me stop sharing here. We'll come back. Don't worry. We'll come back. Share application. Go to Chrome. Okay. Can everybody see the blackboard? Okay. Okay. Good. 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 Okay. So you go under MATLAB programs. Click here to get the MATLAB programs, and it's section 4.1. So just click on that MATLAB program, okay, and it'll download it, and then you bring it into MATLAB. So okay, let me go ahead here and get the MATLAB up here. Let me see. Why isn't mine showing? It should show. Hold on. I'll get mine to show. One moment. Okay, so my MATLAB's coming up here. Okay, so let me see, share application. Here we go. Okay, so I'm sort of using a split screen here. So this is the program. Now the first command is clear vars, and I do that just so when I run the program, I don't want any other variables hanging around interfering with my program, possibly. And then I define symbolic variables m, and I'm using the solve command. The solve command. Okay, so I'm going to solve this auxiliary equation. In MATLAB, you need, when you write the equation, you need two equal signs. I'm going to solve it for m. Okay, and we will copy the code. Paste it in. Okay, and I'm sorry, let me just try to, there we go, hit enter. Okay, and I get my answers. I get my answers, okay? And so there are 5 roots, and that would make sense because the degree of this equation, it's a fifth, or the degree is fifth order, or fifth degree, it's a 5th degree polynomial equation, so I would expect there to be 5 roots. Negative a half, 0, 0, 2 minus 2i, and 2 plus 2i. Okay, are there any questions on that? Okay, so then let me go back to the solution here. Okay, so there are the roots. And now I can construct the general solution. Based off of the roots. let Let me see, question, did I reorder these? I mean, I actually, in the solution here, the order follows the order of the roots. And WebAssign will accept any order. It should accept any order in your solution. So for your assignment for section 4.2, you have over 20 questions, but they go fast when you use the program. They go fast. It doesn't take long to answer these questions with using the MATLAB program to help you. But of course, you know, any second degree, second order differential equation, I mean auxiliary equation, you can always easily, you know, do those by hand, but the of differential equations of order 3 or more, you use the MATLAB program. And so you know, I have to give you enough variety so that you can you know just learn the theory. So, but these problems don't take long. But so here, when we had M1 equals 0, M2 equals 0, okay, when we have M1 equals 0, M2 equals 0, is that case 1, case 2, or case 3? What kind of roots are M1 and M2? M1 equals 0, M2 equals 0. Good, those are repeated roots. So look at my solution here. E to the 0s, which is equal to 1, by the way, plus C2 times S times e to the 0s power. So I have to insert the s here, okay, because you know, I have a repeated root. And then, of course, this whole thing is just going to be s times 1, which is just s. And then I have m3 equals -½ so that's just going to be then, that's going to go e to the -1/2 s. And then finally, I have the two complex roots. And then that forms this portion. Well, these are the solutions here, e to the 2s power cosine of 2x, 2s, and e to the 2s power sine of 2s. Okay, so let me give you a moment to copy that. Okay, now let me ask you this. Thomas says, where is I? Well, that's the thing, Thomas. When you don't have, you see, what we're doing is we're finding a real solution to the differential equation. We're finding a real solution to the differential equation. And so the I is not involved in the general real solution. But you see the 2 and the 2i, this 2 here is your alpha, and this other 2 is your beta. And so if you go back and look at your notes there on case 3 is, in your notes, gives the general solution when you have alpha plus beta I. Good question, good question. I have one question for you, class, and I know we're basically at the end of our class. Suppose you had an M3. Suppose M3, instead of equaling -½ suppose M3 were equal to another 0. Suppose you had 3 repeated real roots. Okay, in other words, suppose m3 were not equal to -0.5, but instead m3 were equal to 0. What would your third solution be? Or I should say the third part be.
Yes.
I would guess C3 S squared.
Good, Justin. C3 times S squared. I'm sorry, yeah, C3 times S squared times E to the 0S. And Hilong and Zachary agree, good. That's right, because you need linearly independence of your solutions. So you have an S squared. All right, so I wanted to do, you have basically what you need to work on section 4.3, but of course you have to worry about section 4.1. That's due this Thursday. And I know, of course, too, you're working on your remedial problems. Let me just see here. Let me make that 4.1 available. So 4.1, of course, now I've reactivated. It's back in there. And 4.3, I've taken off the password. I know there's 1 or 2 students that finished 4.1, that assignment, and so they can work on the 4.3 assignment if they want. Are there any questions on this?
Professor, is the 4.3 assignment also due on Thursday?
It's due on, well, all right, let me stop the recording here. Good question.